Electron energy. So electron energy and electron position are complementary. We know that kinetic energy is 1/2 the mass times the velocity squared. So the velocity of the electron has something to do with its energy. But unlike with the Bohr model where we can say, okay, this is the orbit. This is the path where the electron is traveling nicely. Just, we can predict where the Earth is going to be, a week from Friday. For an electron, the best we can do is what's called an orbital. Now, the word orbital is very similar to the word orbit, but it's not the same thing. An orbital is a probability distribution map showing where the electron is likely to be found. So it's a little bit like that diagram I drew of Andrew. Okay, so there's a such and such probability that the electron is going to be within this volume. And that orbital is going to have a specific energy. And what we find is that many of the properties of the atoms are related to the energies of the electrons within them. So Schrodinger, same Schrodinger who gave us the cat idea, came up with this equation right up here. And this allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location in the atom. And we're not really going to go into using Schrodinger's equation because this is, I would have to study up on this. I don't remember this stuff. When we solve Schrodinger's equation, the solutions are wave functions. And these wave functions describe the wave-like nature of the electron. If we graph the wave function squared, then we can get an idea of the shape of an orbital, that region in which an electron is found. So doing calculations on this, we find that the size, the shape, and the orientation in space of the orbital are determined by 3 different integer terms. And those terms were added into the wave function in order to quantize the energy of the electron. We know from experiment and observation that the energy of electrons is quantized. The emission spectra tell us that. And so the wave function equation has to be quantized. And so those integers are called quantum numbers, and they have names and symbols. So the principal quantum number is n. The angular momentum quantum number is a lowercase l. The magnetic quantum number is m with a subscript l. And then there's a fourth one, the spin quantum number, and that's m sub s. Quantum is where you can't be in between. You have to be in this or in that. It's like, dead or alive. The cat is either dead or alive. You can't be both. You're in first grade or you're in second grade, right?
Or it's summer.
Or it's summer, but then it just depends on the definition. If you define grade you just finished or grade you're starting in the fall, you still have to choose one. So these principal quantum numbers, we need to understand a little bit about them. The principal quantum number n, again, these are all, the first 3 are all integers, meaning they're whole numbers, 1, 2, 3, 4, 5, etc. So this is an integer that determines the overall size and energy of the orbital. And these integers correspond to the Bohr energy levels. So in that diagram that we saw of the Bohr model, there was n equals 1, the first orbital, and n equals 2, the second, and n equals 3. These quantum numbers correspond to the energy levels in the Bohr model. But the Bohr model talks about electrons traveling in orbits, and the quantum model has them in these just regions, these orbitals. So n can be any integer greater than or equal to 1, so it can't be 0, can't be negative. The larger n is, the higher energy the electron has, and the larger the orbital is. For hydrogen, we have this nice simple relationship. The energy of a particular electron is equal to minus 2.18 times 10 to the minus 18th joules times 1 over n squared. So if n equals 1, the energy of an electron with this principal quantum number of 1 is minus 2.18 times 10 to the minus 18 joules. That's for hydrogen, yes. It gets more complicated for the others, but it still works. The energy is negative. Why is energy negative? Because the electron's energy is lowered by its interaction with the nucleus. And lower energy is good. Everything in nature tends towards lower energy, right? Why do rocks roll downhill and not uphill? Because of gravity, but there's potential energy when it's on top of the mountain. The boulder rolls down because in doing so, it lowers its potential energy. Electrons also seek out lower energy situations. The electron, for the electron to have zero energy, it would not be attached to anything. There's an attraction of the electron to the positive charges of the nucleus, and that causes the negative energy. As n gets larger, the energy difference between the orbitals gets smaller. This would be like the rungs of a ladder. Actually, let's just go back to this picture. Where is it? Yeah, that was way too far to go back to. There it is. So as n increases, the difference between these levels gets, that's not a good diagram. That's wrong. Okay, never mind. Oh, there's my picture that I want. It's just on the next page. Okay, here we go. So energy increasing. So if n equals 1, this is for hydrogen. Okay, so you can calculate with that simple equation the energy of hydrogen. And we can do that because we measure the wavelength. And that was what was used to figure out the equation. So for n equals 1, 2.18 times to the minus 18. If n equals 2, the electron in this orbital has higher energy. And n equals 3 is higher, n equals 4 is higher. But the distance between these two is getting smaller. So for n equals 5, we would expect it, oh, that's not a good thing. We would expect it to be closer. The difference between these levels is getting smaller. And that's what I was trying to show with that other picture, but it didn't. Yes?
So n is the orbit?
And we generally think of it as the principal energy level. And I find it very convenient to kind of incorporate ideas of the Bohr model just because it's so much easier to understand, while at the same time acknowledging to myself that they're not traveling in orbits. But yes, this principal energy level or quantum number n is similar to the orbits in the Bohr model.
Is the distance between energy levels, like, can we define that by like a constant number, like from 1 to 2, or is it like just a higher if it goes?
So the question is, how would we find this difference? Well, we can calculate the energy at each level, and so to find the difference, we're just going to subtract.
But is it always going to be the same number? That's what I'm saying. Is the distance always going to be the same?
Between principal quantum number 1 and 2 for hydrogen, it's always the same.
But it's different for other.
But it's different for other elements. Yeah. The next one is L, angular momentum, and this is the one that determines the shape of the orbital. And L can have integer values from 0 up to 1 less than n. So if L is equal to 0, we call that an s orbital. If L is equal to 1, we call that a p orbital. If L equals 2, that's a d orbital, and L equals 3, that's an f orbital. Anybody wondering why we didn't use A, B, C, D? Yeah. Just the way it is. No, actually, there is some historical background on this one. P is for principal, D is for diffuse, F is for fine, and I always forget what S is. But these had to do with descriptions of the lines in the emission spectrum. So before we understood anything about quantum mechanics, there were these letter designations helping to identify. And so diffuse, you could imagine that would be a more diffuse line, and F is a fine line, etc. The magnetic quantum number specifies the orientation of the orbital, the direction in space that it's aligned relative to the other orbitals. And this number can have values from negative L to positive L, including 0. So the number of different m sub L values tells us how many orbitals of a given shape are present. So let's look at L equals 2. So if L equals 2, those are p orbitals. Well, if L equals 2, then the possible values of m sub L range from -2 to +2. We've got -2, -1, 0, +1, and +2, which means there's 5 orbitals. That's not P, that's D. Yeah, I pointed at the wrong thing. L equals 2 is the D orbitals. So this tells us that there's 5 different D orbitals. They all have the same energy. What's different about them is their orientation in space. And we got some pictures coming up. And then the spin quantum number. This specifies the orientation of the spin. Electron spin is a fundamental property. This is a hard concept to describe. The electron is not spinning on an axis like a top, but it can be easier to think of it that way. So Andrew likes to play with Beyblades, and there are Beyblades that spin clockwise, and there are Beyblades that spin counterclockwise, right? And so you can kind of think of the electrons as doing that. You can also kind of think of it being analogous to gender, and so, you know, there's male people and there are female people, right? And they're still people, but there's 2 different varieties. So m sub s can be either +1/2 or -1/2. It's quantized. You can either spin up or spin down, is how we say it. You can't spin in other directions. It's kind of a weird concept among other weird concepts. So the idea here is that each orbital can be described by a set of quantum numbers. And each electron in an atom will have its own unique set of 4 quantum numbers. So if we have quantum numbers n equals 1, L equals 0, and m sub L equals 0, this describes what we often refer to as the 1s orbital. The principal energy level is the first energy level, n equals 1. L is 0. That specifies an s orbital. And m sub L can only be 0. There's only one value, so there's only one s orbital, unlike the d's where there's 5. Orbitals that have the same value of n, we say that they are in the same principal level or same principal shell. So I think of it as being in that first orbit of the Bohr model. That's the lower energy one. orbitals that have the same values of n and L are said to be in the same sublevel or subshell. So here's a picture, an illustration that can kind of help us understand what the heck is going on here. So here are our principal quantum numbers, n equals 1, n equals 2, n equals 3. So for n equals 1, the possible values for L are 0 up to 1 less than 1, which is 0. So there's only one possibility, L equals 0. That tells us that we have an s orbital. For L equals 0, the only possible value of m sub L is 0. M sub L ranges from minus L to plus L. So there is one s orbital. As we'll find in a couple slides, you can put 2 electrons in that orbital. One with positive spin and one with negative spin. And so they're each going to have their own set of quantum numbers. When n equals 2, then we have 2 values that are possible for the second quantum number. It could be 0 or it could be 1. If it's 0, again, that's an s orbital. This determines the shape of the orbitals. And if L is 0, we only have one possibility for m sub L, the orientation. And then we could put 2 electrons in there, one with a plus 1/2 and one with a minus 1/2. Going over here, if L equals 1, now we have more possibilities for m sub L. It can be minus 1, 0, or plus 1. So there are actually 3 of these p orbitals. And they differ in their orientation. One goes up and down, one goes side to side, and one goes in and out, like the x, y, z coordinates. Yes? So this, the m sub L is the quantum number that indicates the orientation in space. And so these 3 orbitals are arranged in 3-dimensional space like x, y, and z axes if you were going to graph something 3-dimensionally. It would be perpendicular to each other.
Spinning, it says here, that's kind of like a metaphor to say that it's angular momentum?
Well, the angular momentum is actually the orientation one. The number. But the spin, there's plus and minus. So the problem is, how do you put 2 negatively charged electrons in one orbital, in one region of space? Why don't they repel each other? Because they have opposite spins. They pair, and so they can cohabitate, if you will. That's why I think of sex or gender, male and female, and they get together. N equals 3. I won't go over L equals 0 and L equals 1, but now we have another possibility for L. It can be 2. So then if L is 2, now we can have minus 2, minus 1, 0, plus 1, plus 2. So now there are 5 different orbitals. Some general observations. The number of sublevels within a level is equal to n. Let's go back to the picture. N equals 1, there's only one sublevel. N equals 2, there are 2 sublevels, S and P. N equals 3, there's 3 sublevels, S, P, and D. So N equals 3, 3 sublevels. The number of sublevels is equal to the number, the principal energy number. Number of orbitals, 2L plus 1. Number of orbitals in a level, n squared. I don't think that those are all that useful, but they're there. So we need to do things like this. List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? Not one. Okay, 5D. What does this 5 tell us?
That's
N. N equals 5.
Oh, n equals 5.
That's the principal quantum number, 5, which tells us the number of sublevels, is 5. So there'd be S, P, D, F, and I think the next one would be G. But this is wanting to know the quantum numbers associated with all the 5D orbitals. Well, D tells us one of the quantum numbers as well. S, P, D, F. S is 0, P is 1, D is 2. So this means that L equals 2. So if L equals 2, then M sub L, the next quantum number, can go from minus 2 to plus 2. So the possible values are minus 2, minus 1, 0, plus 1, and plus 2. So how many 5D orbitals are there? 5. The 5 comes not from this 5, but from the fact that it's D, and these are the possibilities. So we could list the numbers. Maybe let's make a table. No, that's too many, but that's okay. N, L, and M sub L. So N is 5, L is 2, M sub L can be minus 2. The first two are going to be the same all the time for the 5D. Oops, minus 0, that's funny. Those are the quantum numbers for the 5 different orbitals. I know. Okay, so let me tell you about the Electron Hotel. Okay. My husband thinks this is a really stupid analogy, but I really like it. Okay. Oops. He thinks it's dumb. Of course, I think some of the things he uses as illustrations are dumb too, but that's why we're different people. If we agreed about everything, one of us would be unnecessary. Okay, so imagine that this is a hotel. It's kind of a weird hotel. And so this is the first floor, the second floor, the third floor. This is a room, and here we've got 2 rooms, and here we've got 3 rooms. These little boxes are beds. You ever seen a hotel room with 5 beds in it? I haven't. It would have been handy sometimes on our travels because we had to get 2 hotel rooms. Each of these beds can hold 2 people. And you can't have people sleeping on the floor. So in this first room, there can be 2 people. The energy for level 1 is lower. The cost to sleep in this room is less than going up to the second floor or the third floor. So the idea here with the quantum numbers is that each person in the hotel is going to have 4 numbers that identify where they're sleeping. I'm kind of debating in my head. There's different variations. We're going to do the head-to-toe variation of the Electron Hotel. So over here, let's picture this as one of those orbitals, one of these little boxes, right? When we draw orbital diagrams, we typically put the electrons in as little one-headed, or half-headed arrows. So this would be an electron, and here's another electron. This is positive spin, and this is negative spin. And I envision this as the electron's bed. The electrons are people, There's this rule that you can't sleep on the floor, but these are both guys. Guys don't like to sleep in the same bed with each other. Here they're being forced to sleep in the same bed, so they're going to get away from any possible interactions by one sleeping with his head up here and the other sleeping with his head down here. This is actually what they did back in the 1800s in the Army, actually. They slept in these narrow bunk beds, and there were two guys in here, and they sleep head to toe because you fit better in the bed that way. And you slept together because otherwise you froze to death. You needed the heat from the other guy to keep you warm. But anyway, head to toe. And so if this guy's sleeping with his, head up, that's positive. And so this guy's plus 1/2. And this guy's the minus 1/2. And each of these beds is labeled. And so if we had a guy, an electron, sleeping in this bed, we could identify where he is. N equals 3, he's on the 3rd floor. L equals 2, and 2 corresponds to D. He's in the D room, and he's in the -1 bed, and he's sleeping right side up. He's plus 1/2. Every electron in an atom has its own set of 4 quantum numbers. No 2 electrons can have the same 4 quantum numbers. They can have 3 of them the same, because the number for this guy, the first 3 numbers would be the same. N equals 3, L equals 2, M sub L equals -1. But the spin quantum number would be different. So the floor number of the hotel tells us how many rooms there are. On the 3rd floor, there's 3 rooms. The first room has 1 bed, the second room has 3 beds, the third room has 5 beds. Guess how many the next one would have on the 4th floor? 7. 1, 3, 5, 7. Prime numbers. Odd numbers. 1, 3, 5, 7. And then the energy. And so if you think about a group of electrons coming to stay in this hotel, they want to save money. They don't want to stay in the penthouse if they don't have to and pay for it, right? So they're going to fill up the cheaper rooms first. And so let's get rid of these 2 electrons. So if we have a bunch of electrons coming in, the first one's going to sleep upright in that bed, and the next one's like, I'd like to have my own bed, but I'm really cheap, so I'm going to sleep upside down in this bed with this guy. The next one is going to take this bed. Now this 2s room is actually a little bit cheaper than the 2p, and so the next electron will go in there. And then the next electron is going to move over to this room, and he's going to take his own bed. The next electron that is going to come in, is he going to take his own bed, or is he going to sleep upside down with the first guy in room 2p?
Take his own bed.
He's going to take his own bed.
Yeah,
It's like people on the bus. You don't sit next to a stranger. If there's empty seats, you go sit in an empty seat. So the next electron would go here, and then here. Now, once there's one guy in each bed, cheapness, these electrons are stingy. They don't want to spend extra money. The next electron is going to pair up with this guy, and then this guy, and this guy. The next electron coming in, where's he going to go? He has to go to the 3rd floor. The cheapest room on the 3rd floor, S. And the next guy's going to join him, and then here, they're going to take their own beds until they're forced to pair up. And then they're going to move over here. They're going to take their own beds until they're forced to pair up. That at least gives some visual something to this whole crazy idea of quantum mechanical orbitals. Looking at quantum numbers again. Each of these is supposed to specify an orbital, but each of these has one quantum number that's not allowed. We're supposed to replace it with one that is allowed. So this first one, n equals 3, L equals 3, and m sub L equals plus 2. Well, let's go back to our picture here. N equals 3. Okay, well that's allowed. Or was it 2?
It was 3.
It was 3. N equals 3, that's allowed. And what was the next one?
L equals 3.
L equals 3.
Which I don't think it's allowed, is it?
That's not allowed. Because this is 0, 1, 2. There's no 3. To get to L equals 3, you have to go up to the 4th floor. So what's a possible value for L if 3 isn't? It could be 0, 1, or 2. So we can't have we can't have this one. So it could be 2. And then m sub L is plus 2. Is that going to work with this? Yeah. What if we said, well, what the heck? What if I said, well, I'm going to make L equals 1. Is L equals 1 allowed? It's allowed, but then is m sub L being 2 possible? No. So it's got to be 2 here. N equals 2, L equals 1. Those work together? Yeah. What about m sub L equal minus 2? No. M sub L has to be minus 1, 0, or plus 1. Well, in this case, we could do any of them. You have to pick one, but it's going to be one of those. Well, this last one, n equals 1, L equals 1. No, L starts at 0 and goes up to 1 less than n. So that can only be 0. And then can m sub L be 0? Yeah, it has to be. Any questions? So, atomic spectroscopy explained. Each wavelength that we observe in the spectrum corresponds to a transition between orbitals. When the atom absorbs energy, it goes to a higher level. We see discrete lines, specific wavelengths that are absorbed because it can only absorb just the right amount of energy to jump up to that level. If it jumps up to that level, that's an excited level. Excited levels are not sustainable. They're unstable, and it'll eventually fall back down to a lower energy level. It may fall all the way back down to where it was, or it may come down in steps. But every time it comes down to a lower level, it releases a photon of light. The energy of that photon corresponds to the difference in the energy levels that the electron moved. So we can have this electron that was in n equals 1 absorb energy and go up to the n equals 3 level. But it can't stay up there. It's eventually going to relax down. And here, in this example, it comes back down to n equals 2. It releases a photon of light. It's not going to stay there either. It's going to eventually go back down to n equals 1. It's going to go back down to the lowest level that it can. So in the Electron Hotel, it's a little bit like this hotel's maybe in Vegas, and the electron went out gambling and hit a jackpot. He's like, oh, awesome, I'm going to stay in the penthouse tonight. And so he pays for that extra room. And maybe he has enough to spend 2 nights up there, but he can't stay up there indefinitely. It's not sustainable. And so he'll come back down to a lower level. Does that make sense? This energy, this photon being emitted, that's the line that we see. That's kind of redundant to what I already said. We can predict the wavelengths of light for hydrogen. And Bohr and the quantum mechanical model predicted these accurately. But Bohr could only do it for hydrogen. The one electron system is much easier because the electrons don't interact with each other. And this is what we're going to get into on Thursday when we do our experiment. The difference in energy is equal to the final energy minus the initial energy. Delta is always final minus initial. So the final energy is this constant for the hydrogen atom times 1 over the final principal quantum number squared. And then we're subtracting the energy of the initial level. And we can simplify this equation by factoring out the minus 2.18. We get 1 over nf squared minus 1 over ni squared. So what we're going to do is we're going to observe the wavelengths. Delta E is the energy of the light. And we can calculate that from its wavelength using an equation like this, E equals hc over lambda. And then identifying n, f, and ni, we can actually calculate this, which is the Rydberg constant for hydrogen.
We've always used hydrogen.
For calculations like this, yeah, we're only going to use hydrogen because things get really messy math-wise when we deal with more. So these are the transitions that we observe in hydrogen. The ones that fall within the visible spectrum are those from n equals 5 down to 2, and 4 down to 2, and 3 down to 2. The transitions to level 3 are in the infrared, and going back down to n equals 1, those are in the ultraviolet region, and so we can't see those. Determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. We'll do this example, and then no matter what else is after it, we're going to stop. Which is the initial level and which is the final? 2 is the initial, and this n is final. From 2, right? So we're supposed to find the wavelength of the light. Well, we've got that equation. Delta E is equal to negative 2.18 times 10 to the minus 18 joules times 1 over nf squared minus 1 over ni squared. That allows us to calculate the energy of the light. So let's do that. I'm getting tired. So NF is 7. 7 squared. And NI is 2. My voice is getting tired too. Now this will cause some people to miscommunicate with their calculators for sure. Negative 2.18 times 10 to the minus 18 times the quantity 1 divided by 7 squared minus 1 divided by 2 squared. So this is 5.01 times 10 to the minus 19 joules. The wavelength is equal to hc over the energy. So 6.626 times 10 to the minus 34 joules times the speed of light divided by the energy in joules. What happened to, what on that? There's a problem there, isn't there? Is it joule seconds? Thank you. Yeah, okay. There we go. Joule seconds. I'm like, wait a minute. So joules cancel, seconds cancel. This is going to give us meters. 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by 5.01 times 10 to the minus 19 equals sorry, I'm having an argument with my calculator. 3.97 times 10 to the minus 7 meters. Any questions? We will get some practice doing calculations like this in lab. Oh, you need to go home and review? Yeah. One time-saving strategy is to play the YouTube video at 1.5 or 2 times the speed. You can still understand what's being said, but it takes half the time. And then you can, if you want it slower, you can always just pause and change it. Okay, see you on Thursday.